This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning everyone. When you're ready, we'll make a start. So just a reminder that the mid-semester test will be on the 30th of April. Okay, so that's the Tuesday in the first week back from the Easter break. The test will be held during class time, so this time, but in Wilson Hall. Okay, so there's still 3 weeks to go, right, plus the Easter break. So no need to stress yet, okay, but just bear in mind that that's the first thing you'll be doing when you come back from the Easter break. This week everybody should be doing workshop 2 that will run over 2 weeks, okay, so this week and next week, and you'll be looking at different ways of controlling the level in a tank. Okay, so the system you're dealing with is very similar to the one that we've modelled here. All right, and I just want to point out that there was a small error in what I was writing down in the lecture last week. So there was a minus tau missing here in the relationship between the incremental version of the signal V and the incremental version of the signal U. Okay, the nominal equilibrium values of these two signals will obviously be the same, because if you delay a constant, you just get a constant again. All right, so I just wanted to point that out. So we left off last time thinking about the poles of transfer functions and thinking about a transfer function as being the Laplace transform of the impulse response. We saw that we could use partial fraction expansion when given a proper rational transfer function to identify the components of the impulse response. So each pole of the transfer function, so a value of s that makes the denominator equal to 0, gives rise to a component of the impulse response. And the overall impulse response is a sum of those components weighted by the so-called residues associated with each pole. And of course the residues depend on the whole transfer function. All right, so the poles tell you something about the impulse response. It tells you about the characteristics of the components, okay, but to know what the impulse response is overall, you need to know the whole transfer function in order to work out the residues. Okay, so we saw that when a pole has negative real part, okay, then the corresponding component of the impulse response decays as time evolves. If the pole is real, then it just decays as an exponential. If the pole is a part of a complex conjugate pair, but with real part that's negative, it will oscillate as it decays. So the rate of decay is determined by the real part of the pole. All right? Whereas the frequency of oscillation is related to the imaginary part of the pole. Okay, so the larger the imaginary part, the higher the frequency with which it oscillates as it decays in the case that the real part is negative. When the real part is positive, then as time evolves, the component of the impulse response grows exponentially. And if it's part of a complex conjugate pair, it will oscillate as it grows. If it's real, then it just grows exponentially. Okay? When we have repeated poles, then you end up with these exponentially weighted powers of t. Okay? But an exponential will always dominate the polynomial part for sufficiently large t. Right? Remember that the exponential is just an infinite series. It's like it's an infinite order polynomial. So for sufficiently large t, eventually it will dominate. Okay, so if this decays, then overall this decays, right? Even though the t part grows. We didn't look at this last time, but this is just showing what, relating a canonical second order differential equation to a pair of poles. Okay, and we can associate with that pair of poles a so-called damping factor. Okay, and natural frequency. So if you just take the Laplace transform of this, okay, you'll find that this is the transfer function from u to y. Okay, so assuming zero initial conditions, we'll just get s squared y of s plus 2 psi omega n s y of s plus omega n squared y of s equals omega n squared u of s. That's just taking the Laplace transforms of both sides and assuming that the initial conditions are 0. Okay, rearranging this equation here to get ys on us, which is the transfer function from u to y, you end up with this thing here. All right, it's a ratio of two polynomials. It's a 0th order polynomial on the top and a 2nd order polynomial on the bottom. Now you can write down the roots of a 2nd order polynomial explicitly, right? So you would have learnt in high school that the roots of this are given by minus b plus or minus the square root of b squared minus 4ac on 2a. Okay? And you may end up with this being two real numbers or a complex conjugate pair depending on the sign of the bit in the middle. So for this polynomial here, that's what this expression is. All right? A is 1, B is that, and C is that guy there. All right? So in the case that the so-called damping ratio is a number less than 1, okay, then this will always be a negative number, and so you get a complex conjugate pair. All right? The real part of that complex conjugate pair tells you how the corresponding component of the impulse response decays. All right, and we're taking this to be a positive number, right, and we're taking omega n to be a positive number, so that's negative overall, and so we get stuff, a component of the impulse response that decays. All right, the rate of decay is related to the product of the natural frequency omega n and the damping factor psi. Okay, the frequency of oscillation is not just the natural frequency. Okay, it also depends on the damping. Okay, all right. So this is just showing you how all of these coefficients that appear in the ordinary differential equation influence the real and imaginary parts of the two poles. Okay, so the smaller the damping factor, the closer this will be to the imaginary axis. So as the damping goes to 0, these guys will just lie on the imaginary axis at a frequency omega n, because this will just be 1, right, because that's 0. So really, you can see that these things just move on a circle. Okay, so when the damping is 0, you get a pair of poles at minus j omega n and omega n, and as we increase the damping, they move this way. Okay, and when the damping is 1, you get a pair of poles sitting on top of each other on the real axis. So this picture here is just showing you, what the impulse response of a system like this looks like for different damping factors. Okay, so you can see that when the damping is small, okay, you get exponential decay, all right? It takes a long time to decay. That corresponds to this being, I don't know, with them small, okay, because we're saying that's small, and you get oscillations. Okay, how it oscillates depends on the imaginary part, which is not just the natural frequency, it's a scaled version of the natural frequency that depends on the damping factor. Okay, as you increase the damping, you end up with stuff that, you know, doesn't oscillate as much and it decays faster. Okay, so that corresponds to the real parts becoming more negative as you increase the damping factor towards 1. For a damping factor bigger than 1, okay, then you just get a pair of real poles. Okay, all right. So we can use these notions to define what we mean for a transfer function to be stable or unstable. Okay, so the components of the impulse response that are associated with poles in the right half plane are said to be unstable because they blow up as time evolves, right? Whereas the ones in the left half plane are said to be stable, okay, because they decay. Now, the overall impulse response is the sum of all the components. All right, so you only need one component to blow up in order for the overall response to blow up. All right? To end up with an impulse response that doesn't blow up as time evolves, you need all of the poles to lie in the left half plane. Okay? If you end up with a pole on the imaginary axis, okay, then you get a component of the impulse response that persists. Okay, it may oscillate as it persists, or it may just be a step, but only in the case that they're not repeated. If these are repeated, then you end up with you know, these extra you know, you end up with components that look like this, right? So they'll grow, right? Alpha will be sigma will 0, and this will grow with time. All right. Now, the response, the impulse response, is dominated by the poles that are closest to the imaginary axis. All right. Let's take a transfer function that has all of its poles in the left half plane. So all of the components will decay as time evolves. The one that takes longest to decay will be the one closest to the imaginary axis. And so for large T, that's the one that dominates because all of the other ones have already reached 0. Okay? So we call them the slowest poles. All right? Now, if there's a pole in the right half plane, there'll be a component of the impulse response that blows up. If the pole is close to the imaginary axis, then it blows up slowly. If it's far away, then it blows up really quickly. But either way, it blows up. Okay? So for an impulse response to decay, we need overall all of the poles to lie in the left half plane. As soon as there's one on the imaginary axis or in the right half plane, then the impulse response will not decay as time goes to infinity. Okay? So again, we're just giving labels to things so that we can talk about them, these characteristics of transfer functions. So, you know, let me just show you a little video to demonstrate, you know, stability and instability. Okay? You'll be playing with this robot in workshop 4. Okay? You'll be designing the control system that is keeping the pendulum in the upright position. Okay? So what I'm doing here is changing the gain of a feedback controller, right? That's looking at a measurement of the angle and making an adjustment to the voltage applied to a motor. Okay? Initially, the gain is at a value that results in a stable closed-loop system, right? The input that has been applied was me pushing the top. Okay? So initially, the closed-loop system is stable, and when I push it on the top, that's a disturbance, it's an input to the closed loop. you can see that it returns, right? So it's like a little impulse, and it decays, it returns to the equilibrium position. Now I'm increasing the gain of the controller, and as I increase the gain of the controller, what happens is that closed loop poles move closer to the imaginary axis, okay, and it starts to oscillate. And eventually I increase the gain so that we end up with poles in the right half plane, and now the oscillations start to grow, and they grow so much that it makes the system walk along, okay, and that's unstable, okay. So we're getting the impulse response by me tapping the top of the pendulum, okay. You'll be playing with that robot in workshops 3 and 4. Okay, so this is why we care about stability. You don't want the behaviour that we observed at the end. We want the behaviour that we saw at the beginning. All right. So we know that the transfer function is the Laplace transform of the so-called impulse response, right? And we saw that way back here, all right, by starting with the convolution model of the relationship between the input u and a corresponding output. And we saw that you can think of the transfer function as being the Laplace transform of the impulse response. Okay. So let's think about what happens when we put an input in that is bounded for all time. Okay, and see what comes out depending on what the impulse response is. Okay, so we're going to put a signal in, okay, which is just a function of time. This is u of t, and we're saying, let's suppose that we know that our signal t wiggles around in here, but always stays between u bar and minus u bar. Okay, so we've got a bounded input, and we're characterising that input in terms of the bound u bar. Okay. All right. So what will the corresponding output be? Well, the corresponding output at time t is just given by the integral from 0 to t of gt minus tau u tau d tau. Okay, that's true for all t given the impulse response g. All right, so the absolute value of y at time t will be the absolute value, well, of that integral. Okay, and we know that if we take the absolute inside the integral, we'll get an upper bound, right? Because now we're integrating something that's always positive. Okay, so we're always going to get something bigger than we get when doing this integral, because sometimes the integrand is positive and it adds to the integral, sometimes it's negative, okay, which will take away from the integral. So if we take the absolutes in, we always get an upper bound. All right, so that's where this inequality is coming from. Okay, and now we can just do a change of variables. Okay, the change of variables is such that nu is equal to t minus tau. Okay, so you get that d nu is equal to minus d tau. Right, you know that tau is equal to t minus nu, right, as well. So you get that bit there in as the argument of u once you do the change of variables. Okay, the argument, so the upper and lower bounds for the integral change as well. Okay, so when tau is 0, right, nu is t. All right, and when tau is t, nu is 0, and so we're ending up with the integral from t to 0 of g nu u t minus nu minus d nu, right? Because that's what d tau is, right? And so that minus sign, okay, if we take it out, flips the limits of the integral. All right, so it gives us this equivalent bound for the output at any time t. Okay, now the integrand here is always positive. All right, so if I let t go to infinity, I'm just going to get something bigger, all right, which then gives this upper bound once we replace this guy here by its upper bound. All right, the fact that the signal always wiggles around in between this upper and lower bound means that this object here is always less than or equal to mu bar. All right, so if I replace that by its upper bound, I'm always going to be integrating something bigger. All right, and now this is not a function of the argument of integration, so it's a constant and I can take it outside the integral. All right, so we've got this upper bound now for y, the output at any time, expressed in terms of the upper bound for the input and the integral of the absolute value of the impulse response across all time from 0 to infinity. So that bound holds for all t. All right, and we've arrived at it by exploiting information about the input. Right, the information about the input that we're exploiting is that it is bounded. Okay, so let's now suppose that this integral of the absolute value of the impulse response is a finite number. What can we conclude? Well, we can conclude that if that's the case, then y will be bounded for all t. All right, it'll be bounded by this number times the bound on the input. All right, which gives us this result here. Okay, if the impulse response is absolutely integrable, then bounded inputs lead to bounded outputs. All right, now it turns out that you get the other implication as well. Okay, it's both a necessary and sufficient condition for the output to be bounded given a bounded input. Okay, so to see that is not too hard. Okay, so we know that y of t is the integral from 0 to t of g t minus tau u tau d tau. We've seen how we can do a change of variables to rewrite this as like that. Okay, that's what we did up here. All right, doesn't matter that we're, still works with this as the integrand as opposed to the absolute values. Nothing changes there. Okay. Now, let's suppose that u at t minus nu is equal to the sine of g nu, okay, for all values of nu. So I'm now defining what the input is. I'm choosing an input, and I'm choosing the input such that when I evaluate the input at t minus nu, all right, then I get either +1 or -1. So this will be +1 if g nu is positive, okay, or I'll get -1 if g nu is negative. Okay, that's what I mean by the sign. So if I choose u in that way, okay, u will be bounded for all time. All right, it's either +1 or -1. So the upper and lower bounds are just 1 and -1. Okay, so I've constructed a bounded input, And that bounded input is such that the integral here, right, becomes this, right? Because g nu times its sign is just the absolute value of g, right? Because if g is negative, then I multiply by -1 and I get the absolute value. If g is positive, then I multiply by +1 and I get the absolute value. All right? So if I know that bounded inputs lead to bounded outputs, then this must be bounded. Okay? And we get the implication in the other direction. Bounded inputs, if bounded inputs lead to bounded outputs, then this must be true. And this statement is that all bounded inputs lead to bounded outputs. Okay, and we're concluding that this must be true because we've constructed a bounded input, all right, such that the output is equal to this. And if this is bounded for all t, then this must be true. Okay, so absolute integrability of the impulse response is necessary and sufficient for all bounded inputs to lead to a corresponding bounded output. Okay, so when is the impulse response going to satisfy a bound like this? Well, remember, our impulse response is just a sum of, I don't know, the pen's not working, exponentials in the case that the corresponding Laplace transform is a rational function, okay, which it will be if we've, this is the impulse response of a system that was originally described by an ordinary differential equation. Okay, well, what does integrating an exponential function, you know, if I integrate from 0 to t an exponential function, well, let's make that new, right? What am I going to get? I'm going to get e to the alpha k t, 1 on alpha k, minus 1. All right? So, you know, when is that going to be bounded for all time? Right? When am I going to be able to take the t limit here to infinity and end up with a finite number here? Well, I need the real part of alpha k to be negative, right? So that this guy decays as t goes to infinity. If the real part were positive, okay, then you know, this would blow up as I take t to infinity, and I wouldn't have a bound on the impulse response like this. All right? So on the basis of this result here, we can say that all bounded inputs lead to a bounded output if and only if all of the poles of the transfer function lie strictly in the left half plane, which is consistent with what we were saying over here, right? When we were giving the labels stable to poles in that side and unstable to poles in that side. As soon as we've got one pole here, we'll get a component of the impulse response, right, that blows up when we integrate it, okay, which will mean there will be some bounded inputs which, when applied to the system, lead to outputs that are not bounded. Okay, and to get the behaviour that we saw in the video when I tapped the thing, right, I put a little bounded input in and the output remained bounded. But when it was unstable, I put a little bounded input in and it became unbounded. It just kept on growing, well, until, you know, the robot fell over. Okay? So we call a proper real rational transfer function stable if all the poles lie strictly in the left half plane. Now, some people talk about marginally stable systems as ones that have non-repeated poles on the imaginary axis. As far as I'm concerned, that's unstable, right? It's unstable in the sense that there are bounded inputs that lead to unbounded outputs. So let's say we've got a transfer function that's 1 on S, okay? That corresponds to simply integrating the input, right? U to get Y, all right? So if I put a step in, right, what do I get out? Something that grows like that. All right, so I've put a bounded input in, it's always less than 1, and what I get out is something that doesn't remain bounded as time goes to infinity. It also goes to infinity. And here I just have one pole at S equals 0. Right, so to have this property that, you know, all bounded inputs give rise to bounded outputs, you need all of the poles in the left half plane. Poles on the imaginary axis, even if they're not repeated, are unstable from that perspective. Okay? All right. Now, for stable systems with stable transfer functions, okay, we can get the transfer function by taking the Laplace transform of the ordinary differential equation describing the relationship between the input and the output. Or if we know the impulse response, we know the transfer function is just the Laplace transform of the impulse response. So if that's stable, in other words, if the corresponding impulse response is absolutely integral, right, then we often think about the performance of the system in terms of the response to special inputs. Right? An example of the special input is the step that I just put in here. Okay? And if you like, that's a zero frequency sinusoid. Right? So it's not oscillating at all. It's oscillating at zero frequency. More generally, we can think about the inputs to sinusoidal, as the response to sinusoidal inputs. Okay, and we've seen that we can represent oscillating signals in terms of a complex exponential, right? By Euler's formula, the complex exponential can be split up like this, okay, where the real part oscillates like cos omega t, that's like the projection of a point on the circle onto the real axis, okay? So this guy here, as t evolves, is just a point that's whizzing around here, right? This part here is just the projection onto the real axis. This part here is just the projection onto the imaginary axis. So we can use a complex exponential to represent oscillating signals. Now, if you take the Laplace transform of a signal that looks like this is what you get, right? We saw that when we had e to the alpha t, right, we ended up with 1 on s minus alpha. Okay, so it's the same thing now for alpha. We've just got j omega, so that's what appears there. All right. Don't worry about the fact that, you know, this is a complex signal. Doesn't matter, right? It's got two components that are real. All right, and this is the Laplace transform. So we know that if the transfer function is g, right, and we put this signal in, then the Laplace transform of the signal that we get out will be just g times the Laplace transform of this, which is this guy here. All right? So that gives us the Laplace transform of the output. If we know that g is the ratio of two polynomials b and a, all right, then this is the Laplace transform of the output y. We can now take a partial fraction expansion of this to figure out what the components of y will be in the time domain. Okay? So having this bit here is just like having an extra factor in the denominator. Okay? So when we do partial fraction expansion, okay, we get terms corresponding to the factors of a, all right, and we'll get a term corresponding to this guy here, all right, and you figure out what coefficients go on the top by determining the residues associated with this function of s in the same way as we did back here. All right, you multiply the object. Here we were thinking of this as the Laplace transform of a signal, right? The impulse response, right? And we were doing the partial fraction here to figure out what the impulse response looks like in the time domain, right? So the residues were determined by multiplying the Laplace transform of the signal by the corresponding factor and then evaluating the result at s equals alpha k, the value of s that makes that factor equal to 0. So you do the same thing again to get the residues here and here. All right. bk I'm writing here is just the residue that you would get with g, okay? But of course the object we're looking at is not just g, it's g times this, okay? So when we evaluate at s equals alpha k, we get this extra term in the residue. That's why we've got this bit here. All right. The residue associated with this factor will just be the limit as s goes to j omega of s minus j omega times bs on a s, 1 on s minus j omega, right? So that guy goes away and we just get b j omega on a j omega, which is g j omega. All right? Okay, so if we know that the system is stable, then all the alpha k's here must have negative real part. Okay, so the corresponding terms in the time domain decay as time goes to infinity. Right? This component of the partial fraction expansion of this, okay, translates to this in the time domain. All right, we've just seen up here that the Laplace transform of a signal that looks like this is 1 on s minus j omega. So the inverse Laplace transform takes us back. So we get this term here, but now weighted by g j omega. Now as time goes to infinity, this signal doesn't disappear, right? Doesn't go to 0. This is a signal that's whizzing around the unit circle, right? So it persists. Okay? So as time goes to infinity, these go to 0 and we're just left with this so-called steady state part of the response that persists. Okay? So what we can observe here is that when we've put a sinusoid in to a stable system, okay, so a system with a transfer function that has all of its poles in the left half plane, then eventually what we get out is a sinusoid of the same frequency. All right? But it's been scaled, and it's been scaled by the value of the transfer function at s equals j omega, where omega is the frequency of the signal that we put in. So if you like, for stable, for systems with a stable transfer function, sinusoidal signals are invariants in steady state. So if you put a sinusoid in of a given frequency and wait for long enough, what you'll get out is a sinusoid of the same frequency, okay? But that sinusoid will be scaled in magnitude and shifted in phase. Right? So the new magnitude will be the magnitude of g evaluated at s equals j omega, okay? And we'll get a phase shift corresponding to the phase of g at s equals j omega. Right? So evaluating the transfer function at s equals j omega, when we know that the transfer function is stable, tells us what happens to a sinusoidal input, okay, at the output of the system. What we get out is a sinusoid of the same frequency, scaled in magnitude and shifted in phase. All right? Now this works when omega equals 0. In that case, we've just got a step input, all right, because e to the j 0 is just 1. It's this point here. Okay, so we just get a step in. And so if we know that the transfer function is stable, then when we put a step in, right, that's u to the system, what we get out is some transient response, but eventually all of the transients die away, okay, and we're just left with a step out, and the size of that step will be g evaluated at s equals 0. Okay, but it has to be a stable transfer function for all this to work, because we're relying on all the transient parts going to 0. As soon as there's a pole in the right half plane, then there will be a component here that does not decay. In fact, it will blow up. And so what you'll see at the end is not a steady state response. You'll be going to infinity one way or another, perhaps in a way that oscillates. Okay? All right, so that's what stability is really about. And this is called the frequency response, right? For the obvious reasons, because it tells you how a sinusoidal input will be affecting the output in steady state in terms of how that sinusoidal input gets scaled in magnitude and shifted in phase. Okay, now let's spend some time thinking about the zeros of a transfer. All of our attention so far has been on the poles, right? Why? Because the poles tell us a lot. They tell us about the components of the impulse response. And in particular, it tells us, you know, the real part of the poles tells us how long it takes for each component of the impulse response to decay, right? The slowest one, the one with the real part closest to the imaginary axis, is the one that takes longest to decay, and that will dominate the response. Okay? But how they all get added together depends on the whole transfer function. In other words, it also depends on the zeros. Right? So the zeros are important as well, okay, from the perspective of understanding what the transient looks like. Okay? And this little example here is about trying to build some intuition around the impact of the location of a zero in the complex plane on the transient part of the response. So let's consider this transfer function here, okay, and we're going to put a step in, right? So it's a stable transfer function. It's got a pole at s equals -1. It's got a pole at s equals -2. They're both in the left half plane. So we've got a stable transfer function. So from the analysis we just did, we know that if we put a step in, then in steady state we will get a step out. And that step out in steady state will have magnitude g evaluated at s equals 0. So if we evaluate this transfer function at s equals 0, what do you get? Well, you get minus c divided by c, which is just 1. Okay? Now this plot shows the response to a step input for different values of c. C being the zero of this transfer function. If I put s equals c in here, I get 0. Right? So that's how we've defined the zeros. So this is showing the response for different values of the zero. Changing c doesn't change the poles. Right? So this is saying if I put a step in, then I get a step out of size 1 in steady state. That's why they all go to the same value. Right? The amount of time it takes for them to all go to that value is roughly the same, right? Because changing c doesn't change the poles, and how long it takes for the transients to expire really just depends on the poles. Okay? So it's dominated by the slowest pole, and the slowest pole is the one at s equals -1. There's another one at -2. Right? So this decays much faster than this. Right? How long it takes to reach the steady state value is really dominated by this guy here. All right? So what can we observe? Well, let's consider the case where C is a positive value. Okay? So when C is a positive value, we're getting a 0 in the right half plane. All right? And when C is a small value, meaning we're close to the imaginary axis, we get a transient part of the response that does this. Okay? It ends up at 1, like all of them do, okay? But we're getting this large undershoot, okay? And I'm using the term undershoot to mean that it moves in a direction opposite to where it ends up in steady state. Okay, it's not the fact that it goes down, it's the fact that it's going down when the steady state value is up relative to where we're starting. So if we put a minus sign in front of here, we would get everything flipped like that, and it would still be undershoot because it moves in the direction that's opposite to where it ends up relative to where it starts. That's what undershoot means. Okay, and as we increase C, okay, so moving the 0 further to the right, we can see that the amount of undershoot seems to decrease. Right, so when the 0 is very close to the imaginary axis, we get a lot of undershoot. Okay, as we move it further away, we get less undershoot. Even when C equals 10, if you zoomed in here, there would be a little tiny bit of undershoot before it starts moving in the direction where it will end up. Okay, so it seems that zeros in the right half plane give rise to undershoot in the transient part of the response. Okay, just from this example, and you can't draw too much of a conclusion by looking at just one example, but I'm just trying to build some intuition and we'll do some analysis in a second. All right? So if, on the other hand, the 0 is in the left half plane, so if this guy is now in the left half plane, so in other words, if C is a negative value, then what happens is when C is a small negative value, okay, so sitting closer to the imaginary axis than the dominant pole, we seem to get overshoot in the transient part of the response, in the sense that during the transient you go past where you end up. That's called overshoot. But as that 0 is taken further into the left half plane, okay, we eventually get no overshoot, right? So if we move it further into the left but still to the right of the dominant pole, then we get some overshoot but less. And once it crosses over to the other side, you get no overshoot at all. Okay, so this is just an example to build up some intuition. Okay? Now, for some analysis. Okay? So let's suppose we're working with a transfer function. It's stable. Let's suppose that its DC value is 1, right, as in the example. And let's suppose that there is a 0 at s equals c. And let's suppose that that's positive valued. Okay? Now, let's define the settling time to be the amount of time it takes for the output to wiggle within a small band of the final value. Okay, so that's going to be determined by the poles. Right? It's going to be determined by the slowest pole, the one closest to the imaginary axis. It's how long it takes to get close to the steady state value. Right? So Ts really just is a function of the poles. All right? Then in that case, you can put a lower bound on the amount of undershoot that you get. Okay? And that lower bound is determined by the location of the 0, okay, and the time constant. All right? So the smaller this is, okay, then the bigger the lower bound on the undershoot. So for small values of the product C and Ts, you'll always get large undershoot. Okay, and that corresponds to the 0 being close to the imaginary axis, much closer than the dominant pole is to the imaginary axis. That's how you get a small value of C, TS. Okay, remember TS will be, it will be 1 on the pole. Okay, so the way we get a small CTS is by the 0 being closer to the imaginary axis than the dominant pole. All right, now this bound just comes from some analysis, and this analysis, rather than looking at this signal, looks at 1 minus the signal. Right? So it looks at 1 minus the signal, so just, this flips around, right, and we bring 1 down to the origin. Okay, so it's the same thing. All right. Now, the advantage of working this is that we now have an upper bound for this signal, right? It'll be 1, right, plus the amount of undershoot we have. Okay. All right, so we can use these bounds, and the fact that beyond TS we have another bound for that signal, it always wiggles between plus and minus delta, right, to derive this relationship, okay, from which the bound follows. Okay, let me just show you what it is, and we'll pick this up next time. But here's how this analysis leads to the bound that was written at the top of the slide. Have a look at that before Thursday, and we'll pick up from here at that time. Okay?
There's a question from the mid-semester of 2018. I'm not able to match the answer which is here. I'm getting, I think, math mistake. Instead of 6, I'm getting 3.
Well, I don't know, you must have made a mistake somewhere. These have all been thoroughly checked a million times, so you can't use this solution to figure out where you've made a mistake.
Because in here we have a 3 by 2, and this is u is 1 by 2. So, and u dot is
1 by 2.
1 over 2.
Oh, yep.
So when you substitute, this would become 0, and inverse of it makes 2 to get cancelled instead of getting 6. So instead of getting 6 here and there, you get a 3 at both the places. Sorry, I made a mistake, so it's a square.
It's squared, that's why. Yep. It's squared. Because 1 over the derivative, right, is... Yep.
I need to check this also.
Because this is the derivative, right?
Yeah, it's a derivative.
Right? So you've started off with this, right? And you've taken the derivative of this with respect to x. That. That's where you get the squared from.
I was only checking this minus, but I haven't checked the square.
Well, because you haven't taken the derivative either, right? So, yeah.
And one more question from today's lecture. What if the 0 is exactly on the origin? Like on the intersection of the imaginary axis and the real axis.
Well, what's g of 0 going to be then?
It's going to be 0.
Yeah. So what's the steady state response going to be?
It's going to be a straight line.
No.
Increasing.
What's the steady state value of the output? It's this. G at 0.
It's 0.
So if you're saying you've got a 0 at 0,